Sorry, I lost the recording there a bit. My limit is equal to 1. And this is the case where the root test is inconclusive. Using this test alone, I cannot tell whether or not the series converges. Now, for this set of problems, I'm mainly interested in practicing the root test. For this problem, since my root test is inconclusive, I would need to use some other test. Now, I might use the basic divergence test. I say that this summand formula, 2n squared plus 1, all on n squared, and raising that to the power n, well, in the limit, as n goes to infinity, I'm taking very large powers of a fraction that's bigger than the number 2. So that's going to go to positive infinity. Although the root test was not able to tell me about the convergence of this series, the basic divergence test tells me that the series diverges. Diverges by basic divergence test. If your summands do not go to 0 as n goes to infinity, the series has to diverge. All right, well, let's look at another series. The next one I want to look at is the sum n starting at 1 going to infinity. Now I've got n to the power 4 minus n cubed, all divided by e to the power n, and this whole fraction is raised to the power n. So once again, I'll be calculating a limit as n goes to infinity, and I take the nth root of the absolute value of this formula. So this time I do have subtraction in the numerator. That's something to be aware of. But for whole numbers, starting at 1 and up, this numerator, okay, well, 1 to the power 4 minus 1 to the power 3, that's 0. But then for 2 and up, n to the power 4 is going to be a larger number than n to the power 3. So this numerator won't ever give me a negative number. Now, in my limit calculation, I've written the nth root as this 1 over n power, and that will combine nicely with the nth power that I see. And by combine nicely, I mean that they will cancel exactly. And what I was saying before is that this numerator is never negative. So once again, I have a problem where the absolute value bars were just redundant for the series that I wrote. And that's okay. Now I need to compute this limit. Numerator n to the power 4 minus n to the power 3, denominator e to the power n. And I claim that this is a job for L'Hopital's rule, where the numerator and the denominator of my fraction are both going to positive infinity. Well, that's pretty clear for the denominator. As n grows, e to the power n grows very quickly. But for the numerator, n to the power 4 and n to the power 3 are both going to infinity. And then I'm taking the difference of those things. So you might be reasonably concerned that this is my infinity minus infinity situation on the numerator. That is indeterminate. I need more context to understand what's going on. Well, I would suggest factoring this numerator. So I can rewrite it as n to the power 3 times the polynomial n minus 1. And now both of these factors are going to positive infinity. The product has to go to positive infinity as well. That's my justification that the numerator and denominator both go to positive infinity. And what that allows me to do is to simplify my limit calculation by replacing the numerator with its derivative. I'll get 4n cubed minus 3n squared, all divided by e to the power n, since the exponential function is its own derivative. Okay, then I still have a polynomial divided by an exponential function, and the numerator is still going to positive infinity. I'll need to do that factorization trick one more time, maybe 2 more times, in order to justify using L'Hopital's rule again. But I can see that I would have 12n squared minus 6n to the power 1 divided by e to the power n. And then I'd use L'Hopital's rule again, and I'd use it again. And eventually I'll get down to the limit where the numerator is just a constant, 24, and the denominator is still e to the power n. Now, the numerator is a constant, but the denominator is going to positive infinity, so this limit will be equal to 0. What this tells me is that the series I'm looking at is convergent. I calculated the limit of the nth root of the nth summand in absolute values. As n goes to infinity, I got a number less than 1. So the root test tells me this series converges. Here is another problem to look at. I'll take the sum, n starting at 1 and going to infinity. And again, I'll have some formula all raised to the power n. I wrote these on purpose to be very applicable for the root test. The numerator is going to be sine of n plus cosine of n. And the denominator is going to be the square root of n. That whole fraction raised to the nth power. So this time, my numerator is producing positive and negative values. It's a bit difficult to predict exactly where those will be positive and negative because the trig functions don't play that nicely with whole numbers. Multiples of pi, sure, but just regular whole numbers gets tricky to work with. But I'm still taking the 1 divided by n power, the absolute value of this fraction raised to the power n. So I'm still going to get that very nice cancellation. So I'm looking at the limit. Here, the numerator is the absolute value of the sine of n plus the cosine of n. Since the denominator is a square root and square roots are always positive. I don't need the absolute value bars there. And I want to figure out what happens in the limit as n goes to infinity. Well, like I was saying before, this sine of n plus cosine of n is difficult to predict. And now at least I know that that's got to be a number that's positive because I'm using absolute values. But what else can I do? Well, what I'm going to do is I'm going to use the squeeze theorem. Because when I work with the trig functions, sine and cosine, even if I can't predict exactly what number they're going to be, I know that the very largest that either of these functions gets to be is positive 1. And so if each of them has to be less than or equal to positive 1 on its own, together their sum has to be less than or equal to positive 2. And now the squeeze theorem requires that I have a lower bound as well. And since I'm using absolute values here, this numerator has to be less than or equal to 0. Okay. So this limit that I care about is squeezed between these other two limits with easier formulas. The limit on the left is just going to 0, since the numerator is 0 no matter what value of n is. That'll always produce 0. For the limit on the right, I once again have a constant divided by a function which is going to positive infinity. A little bit slower, right? The radical n is a slower growing function than the exponential function, but it does go to positive infinity. So the limit that I care about, well, it has to be less than 0 or equal, and it has to be greater than 0 or equal. The only way I can satisfy both those conditions is that if the limit is exactly equal to 0. So I've calculated my limit. The limit I got was exactly 0, which is less than 1. The root test tells me that this series is convergent. Okay, let's move on. Tidy that up a bit more. Yeah, there we go. Okay. The next one I want to try is the sum. Again, n starts at 1 and goes to infinity. Now I've got n to the power n divided by e to the power n. Since we've been doing a couple of these already, you probably see where this is going to go, because everything in my formula is raised to the power n. I'll be able to use the root test, and the limit that I calculate will be fairly simple. Taking the 1 over n power of n to the power n is just n. And taking the 1 over n power of e to the power n is just e. And once again, both of these quantities are positive. So the absolute values are redundant for this problem. Okay, well, my numerator, n, is going to positive infinity. My denominator, e, is just a constant, right? E is just an irrational number slightly bigger than 2. So this limit is going to be infinite. It's going to go to positive infinity. Now, I didn't get a real number for the value of this limit. But because I'm able to determine that this limit goes to positive infinity. I can still say positive infinity is greater than 1. And so the root test does give me an answer here. The root test tells me that this series is divergent. Even though the limit gave me positive infinity, that's still good enough for the test. I'm putting my word divergent here in green letters because it's a successful application of the root test. This is unambiguous. The series I'm looking at diverges. So good job. The very last problem I'd like to look at here I'll take the sum from n equals 1 to infinity, numerator, again, n to the power n, and denominator, sine to the power n of n. So here, I'm being pretty tricky when I wrote this problem. Let's take that limit for the ratio test. The limit as n goes to infinity. I want the absolute value of my formula. And then I'll take the nth root, or the 1 over n power. Those operations mean the same thing. Well, once again, n to the power n, and then raised to the power 1 over n, is just going to be n, right? I'm taking the nth power of this quantity, then I'm taking the nth root of the same quantity. Those operations cancel each other out. And I would have absolute values here, except that once again, my n is a whole number, so that's redundant. Now in the denominator, we get a different story. For the denominator, well, I've got sine to the power n of n. This is our standard way of writing powers of the trig function. So even though it's written as an exponent on the sign, on the word sin, this is the nth power of that whole function. Taking the 1 over n power is going to cancel that. So I'll have just ordinary sine of n. This time, I do need those absolute values because the sine function produces positive and negative outputs, and sometimes 0 as well. So this does raise a question. Could I be dividing by 0 here? I wouldn't like that. I could do it once or twice, because in the limit, I only care about what happens as n goes very large, but still of some concern. Fortunately, I know exactly where sine is going to produce an output of 0. And that's only when the input of the sine function is a multiple of pi, right? 0, pi, 2 pi, 3 pi, 4 pi, and so on. And what's particular about all of those numbers is that they are irrational. They can't be written as fractions of whole numbers. Well, that means that they can't be whole numbers, right? Irrational numbers are not whole numbers. And since I'm only looking at whole numbers here, then I'm fine. No matter what n is, this sine function will never produce exactly 0. It might get close, but it won't give me exactly 0. Okay, so how do I compute this limit? The numerator n is going to positive infinity. the denominator is always positive, absolute value of the sine of n. So what I'm going to do is I'll say that whatever this limit is, well, it's going to be greater than or equal to a different limit where my numerator is still n and my denominator is 1. Well, what happened? The sine function is bounded. The very largest it can be is positive 1. The very smallest it can be is negative 1, but I'm using absolute values. If my denominator is a number smaller than 1, the effect of dividing by a number smaller than 1 is that I've made the numerator larger. So the limit that I care about has to be larger than a limit where the denominator is always 1, right? Making the denominator larger makes the fraction smaller. Well, this formula is easier to work with because I know that the limit as n goes to infinity of n, the limit is infinity. That is nearly a redundant statement. So this limit here has to be a quantity greater than or equal to positive infinity. And there's only one quantity that could be, positive infinity. So once again, I've calculated my limit and I got, well, I didn't get a real number, but I got positive infinity, which is greater than 1. So the root test tells me that this series is divergent. And we're done.